Right. Oh, Victoria. All right, everybody has a copy of all the goodies I handed out last time, including the extra credit. 2 extra credit exercises.
You gave handouts all the way to 3, right?
I'm sorry?
So you gave handouts all the way to 3 or more. I only got it to 3. So
Chapter 4 and 5. You don't have 4 and 5? That's what we're doing today. You probably have this.
yeah, I got a chart, but I'm still.
You got this one from the other place too. And you got one already? Chapter 4 and 5.
Yes, I got that.
Okay. Okay. So we're going to do at least in chapter 4 today. Don't forget to sign in. Did it when I wasn't looking. I'm sorry? Okay. All right. Chapters 4 and 5 will constitute the exam 2, and that's scheduled for September 12th. So we got 9 days. And we're going to get, this week, we're going to get 4 and 5. We've got a buffer day built in, so we shouldn't have to rush. All right. So we're gonna look at the foundations of chemistry, including the vocabulary and basic concepts that underlie everything that tells chemistry what to do. The elements, well, we got a full periodic table now. Everybody's got a name, all the way up to 118. I had to put these in here because this version didn't have anything but those spots. Okay, but now they all have names. So we have 118 named elements on the periodic table. This says 88 are found in nature. Actually, there are more. Perhaps as high as 98 are found in nature. Some of them were originally identified and isolated from man-made sources. In other words, they came out of a nuclear reactor. That's the only way you can make a new element. But our analytical techniques have since become more refined, we can detect at much, much lower concentrations. So some of those that were man-made, we're finding them in nature. Okay. As you may already know, each one of the elements has a symbol. And some of them only have one letter, always capitalized. If we have to go to 2 letters, then only the first letter is capitalized. For instance, sulfur is already taken, so when we get to selenium, we have to add a letter just to cover our bases. Usually, the ones with single letters were found first. Back in the Middle Ages, most of them. So, this is what you might think of as the alphabet. And I've given you maybe half of them to memorize. You don't have to memorize all these guys down here, except for uranium and plutonium, because they're so important historically speaking. But once you know those, then we're going to figure out what to do with them. And that's going to involve naming compounds. How do you put the elements together so that they're properly balanced? And then how do they react? So we'll get around to that. This chart is out of your textbook, or out of this textbook. I think the textbook you have now might be have a little different numbering scheme. But originally the table came out of the textbook. And you'll notice that by mass, remember what mass percent is. Just in this case, it's the mass of the element. Percent by mass is just the mass of the element divided by the mass of the sample. So however much element you have in the total amount that you're sampling times 100 is the percent composition. And this is in the Earth's this is everything. This includes the Earth's crust, all the oceans, and the atmosphere. We don't go below the crust. Down there it becomes less interesting.
What did you say that was drawn?
Which one?
What is that? What?
This is mass percent. Mm-hmm. So, the mass of the element in these 3 environments is oxygen, right? So, why do you think that is? Why so much oxygen? Well, there and there. Water is 2 hydrogens and 1 oxygen, right? So you got lots of oxygen there in water. Plus the atmosphere is 20% oxygen. Okay. What you may not know is in the Earth's crust, most of the elements, at least the metallic elements, are combined with oxygen in the crust. So when we want to produce iron to make steel, we've got to separate the iron from the oxygen, because it's primarily 3 oxygens and 2 irons. So there's lots of oxygen everywhere. Sometimes it's free in the atmosphere. Sometimes it's combined in the oceans or in the Earth's crust. Silicon is number 2. Right? Where are you going to find silicon? Well, you won't find a whole lot of it in the oceans. You won't find any of it, as a matter of fact, in the atmosphere. But you will find a huge amount in the crust. Just walk out on any beach, you know, and wiggle your toes and you're down into silicon dioxide. That's sand. And then you have lesser amounts of the other elements. Aluminum's pretty high amount. Iron, of course, is pretty high. But then you go on down lesser and lesser and lesser amounts. What do we mean when we say element? An element is the simplest let's look at, let me take another tack. If you have a sample of anything and you start dividing it, and you just keep dividing it and dividing it, first physically, and then you can use chemical means to start separating whatever's there. Eventually you get to the point where you separated things and you cannot separate them any further. Right? You can't break them apart, either physically or chemically. At that point, you have an element. And it has definite characteristics, physical properties and chemical properties. And it's well defined and distinct from every other thing that we would call an element. Okay, and it's represented by a symbol. And it has a name, of course. Now, that element could be one atom. It could be a billion atoms. But all the atoms are physically and chemically similar. I can't say they're exact, and I'll tell you why eventually. They're not exactly the same. The element could be a combination. For instance, all of these noble gases exist as separate atoms. You may have a lot of them together, but they're all separate atoms. There are some elements that exist under normal conditions of room temperature and pressure and atmospheric pressure. They exist as diatomics. They always come in pairs. Two atoms together, but they're the same atom, so they're the same element.
Is there a group of them, or is there a group of?
Yeah, just a few of them. So when we say hydrogen on the Earth's surface at 1 atmosphere pressure, we always mean 2, H2. 2 hydrogen atoms attached together. Hydrogen, nitrogen's always diatomic, oxygen, fluorine, chlorine, bromine, iodine. They're all diatomic. So you just have those few. That one and these are diatomic. So that's important for solving problems, because if you read a word problem and it just says the name, and in order to solve the problem, you have to write an equation with that element in there, you better write that element as a diatomic or it'll never balance. Okay. I'll keep hammering at them, so brace yourself. Now these elements can be combined. Let's see, where was I going? Some of them are diatomic. Some of them actually are ionic when you isolate them. For instance, in the body, you're going to have, well, whenever you see a lab report that comes back on your blood work, it'll have a list of, at some point there, they'll have a list of electrolytes. Right? Sodium, potassium, calcium, magnesium. They might even have chloride in there. And those should fall within a certain range if you're not sick. Sodium is one of them. It's going to occur in your body as the sodium ion. Okay. Chloride will occur in your body. Well, in your blood, I should say. It'll occur in your blood as an ion. Now, it can occur elsewhere in the body combined in a compound, but for argument's sake, that's an element. It happens to be an ion, but it's still a chlorine element. Okay. I mentioned those before. Each element has a unique symbol. First letter is always capitalized. In other words, if we say, I want to write aluminum, that's not aluminum. That's Alabama. Okay. It needs to be one capital and one small. Okay. Now, I'm not sure if I give you a history lesson on this one. Okay. There were a whole host of different proposed groups of symbols to be used to represent the elements. They went from the sublime to the ridiculous. Fortunately, the one that won out was the simpler, more logical one proposed by let's see, where was he from? Sweden, I think. Berzelius. He proposed our present method, and I'm glad he won because some of the others are really weird. So he just said, let's just use letter symbols. You know, keep it simple. Your book might go into more detail about him than I've got time to. So O for oxygen, Kr for krypton. What if we only have one K? It's not krypton anymore, right? Well, it's potassium, right? Yeah, potassium or kalium for the Latin. And did I mention that before? Some of the letters are based on the Latin or the Greek, right? You've got a few of them, not a lot. Sodium for natrium. Let's see. Fe is iron, right? So we don't start with IR. If we used IR for iron, we get it confused with iridium. So we use ferrum, which is Latin for iron. Let's see. Argentum for silver. Aurum for gold. Hydrogenum, I think that's mercury. Let's see, who else? Lead, plumbum, which is Latin for heavy. SN, stannum for tin. Stilbium for antimony. There are probably several others. Ah, that's a good one. W, tungsten. It's the Latin wolfram. Okay. But most of them can be traced back to their English names. And this is an alphabetical list. Your textbook most textbooks usually have two. They have the periodic table and they have an alphabetical list. I don't rely on the alphabetical very much, because the periodic table gives you so much more information at just a glance. And that as we go, we'll add things to it that help make it more intelligible. We didn't just slap these things up there like that, just throw them on the board and they landed that way. They're in those positions for very good reasons. And they allow you can tell things about the structure of each one of the atoms in here based upon where it is in the chart. Okay. So up to this point, up to the time of John Dalton, who was an Englishman, he lived in, I think, 17th century. We had developed laws that governed how we thought about things and how we thought about reactions. And we'll go back, we'll introduce some of those laws at some point. But as far as the why atoms are the way they are, it was Dalton who came up with the first theory. So he didn't just say, this is what happens, this is why it happens. Oops. There. Now, when we talk about, I know we mentioned this earlier, pure substance. Pure substance is something that's got nothing else in it but the one element or compound. Pure substance, an element might be gold. Pure substance that is a compound might be water. And then mixtures would be combinations of the pure substances. And he said most materials in nature are mixtures of pure substances. You rarely find a pure substance. Of course, gold nugget, that's a pure substance. Let's see, what's another pure substance? I can't think of it. Not right offhand. He also said that pure substances are either elements, that is, there's no other type of atom in there but that element, or they're compounds. They're actual joining of elements into a new substance. And when you make a compound, it completely changes the physical and chemical behavior. He also said a compound, which has to be at least two or more different elements. And the reason I say that is because that's not a compound. It has two atoms in it, but they're both the same element. So that's one of your diatomics, hydrogen. Okay? You have to have at least two elements in there. Then we add an oxygen and two hydrogens. That's water. Now you have a compound. He also said that, and at this time, all they knew, all the chemists, or they didn't actually call themselves chemists, they called them natural philosophers. But all they knew at this time was mass. How much did each of the elements weigh? They could degrade a compound into its elements and weigh the products. But they didn't know how many atoms that represented. They only knew mass. So the first set of laws that you get relate to mass only. But Dalton said a given compound always contains the same proportion by mass of the elements. That means that no matter what the source of the compound, say you purify water so that you will only have that, it's going to have a ratio of some mass of hydrogen to a mass of oxygen. If, however, you say you burn hydrogen in air, you combine hydrogen and oxygen, and you make water. Right? The biggest hydrogen burning I ever saw was the launch of a space shuttle. That big orange tank on the outside, it's really two tanks inside. One of them has liquid hydrogen, one of them has liquid oxygen. And in the engines, they combine them. You get lots of energy and water. So what Dalton is saying is that no matter what the source of water, whether it's from the space shuttle engine or from purification, that water will always have the same ratio by mass of hydrogen to oxygen. Okay, that defines the compound. That's known as the law of constant composition. Okay, so there we have a law, and we can't say why that is. Of course, now we know that it's because two atoms combine with one atom, 2 to 1. And that establishes the ratio of atoms, and since each atom has its unique mass, then that also establishes the ratio by mass. That's part of the theory. But at this point, they only knew the law of constant composition. Okay, so in this case, they knew that 8 grams of oxygen combined with 1 gram of hydrogen. Okay?
How did they figure that out?
They used chemical means to break the water apart and weigh the products. Now, the products are going to be hydrogen. They probably break it apart as hydrogen gas, so they have to catch it. And they have to know the weight of the container first, and then the weight of the container after. They can tell how much hydrogen it is. They could probably do the same thing with oxygen, or they could combine it, oxygen, with something else and make an oxide and weigh that. But then you need to know how much of the, usually a metal, was combined with the oxygen, so you could subtract out that weight, and what's left over is oxygen. But there are methods to do that. And you can determine the mass ratio of each one, because if you know the mass of the total when you start, then the ratio is just a percentage of what you started. Okay. Carbon dioxide, they could establish that 2.7 grams of oxygen for every 1 gram of carbon. Right? That's all they knew. They didn't know that the reason for that is that you have 1 carbon atom and 2 oxygen atoms together. This explains why. That's just the law. This says why it happens. Oh, made a boo-boo. Dalton wasn't 17th century. He was late 18th, early 19th century. Okay, so now we're going to get Dalton's atomic theory step by step. What are the premises of Dalton's atomic theory? He kind of, yeah, I guess it's safe to say, he stole this one from the ancient Greeks. Because they also believed, the ancient Greeks also believed that everything was made of tiny particles. And they called them atoms. They called them atoms because in Greek, tomos means to cut. And anything preceded with an A means not. It's the opposite. It's the negative of the word that follows it. So it means not cut. That just means that this atom, this particle, can't be cut any further by physical or chemical means. That's the smallest you can get. Okay? Of course, now we know that you can break atoms apart into elementary particles, but they didn't know that. And, well, that's where the similarity stops, because the ancient Greeks thought that everything was made of the same atom. And you had to introduce other factors to make substances different. So you had the four basic elementary forces like earth, air, water, and fire. But what Dalton said was that the elements are made of atoms. And let's see, it's the second one. All atoms of a given element are identical. They're different than other elements, but they're the same for each element, right? So the elements of bromine, atoms of bromine will all be the same. That's why bromine behaves the way it does, whether you have this amount or that amount, because the atoms are all the same. It doesn't matter how much you have. It behaves the same. And of course, like I just said, the atoms of one element are different than the atoms of the other. That's where Dalton differed from the ancient Greeks. He said these atoms are the same for this one, but they're different for this one. That explains why they behave differently. So, how do we get compounds? Dalton said we get compounds, we get different substances if two elements come together, two or more actually, come together and they react with one another, they can produce a combination of those elements we call a compound. And then the physical and chemical characteristics of the compound are completely different than either of the elements that came together to make it. So you get a different substance, a pure substance. You start off with a pure nitrogen, and you start off with a pure oxygen, and they come together and make this one. That's one form. If they come together and make that one, though, they got the same elements in there, but they're in different ratios, right? And this one is also a different ratio. So you can get three different compounds out of nitrogen and oxygen, right? Nitrogen monoxide, nitrogen dioxide, and dinitrogen monoxide, which is laughing gas, nitrous oxide. And these compounds owe their different physical and chemical behaviors to the ratios of the elements as they combine. You don't get the same effect in the dentist chair from this one that you do from that one. In a chemical reaction, when you get elements combining to form compounds, or even when you get an element and a compound reacting, or two compounds reacting, all you're doing is rearranging the atoms. You don't create atoms, you don't destroy atoms, you just rearrange them in a chemical reaction. And when you have the reactants come together to make products, the products are going to be different than the reactants, but you're still going to have the same atoms that you started with. It's just that when you form a different compound, you create different physical and chemical properties in the process. Okay. Now, this question is a little premature, I think, because you haven't been given information. But I'm going to take the slides in order. Elements are made of tiny particles called atoms. Yes, that's still true. All atoms of a given element are identical. That's not true because of isotopes. Okay? And we're going to go into the structure of an atom and explain what an isotope is. But the short version is two different isotopes of the same element are indistinguishable chemically. That is, they react the same. But one has a certain number of neutrons, the other has a different number of neutrons. So they're not, technically speaking, identical. A given compound always has the same relative numbers and types of atoms. That's true. So 1 and 3 are still true, 2 is not true. And atoms are indestructible. That's not true either. Now, in a chemical reaction, that's true. You don't create or destroy matter. You don't change the elements in a chemical reaction, but the atoms are not indestructible. All you have to do is put them in a nuclear reactor and see what happens to them. Or put them in a particle accelerator, you know, and smash your target with, oh, I don't know, what do they use? Protons. Protons accelerated almost to the speed of light. What's the name of that? Large Hadron Collider on the French and Swiss border. They accelerate large particles to huge speeds, smash them into targets, or they get them going both directions like this, you know, and then they smash them together. So it's like my car's going 50 and the car approaching me is going 50. That's like hitting a brick wall at 100 miles an hour. Okay, so sometimes you can gain more energy by counter-rotating your particles, and then at the last second, you just tweak the confining magnetic field and put them in each other's path. Bam! Get a nice big subatomic explosion. And you destroy the atoms. Okay? That's the whole point. You destroy the atoms because you want to see what they're made of, the subatomic particles. Okay, so that one's still true and that one's still true. So we describe a compound as a combination of two or more atoms, actually two or more elements and their respective atoms. And we use a chemical formula to define them. I think I need to, let's see. Let me look ahead just a little bit. Okay, we're going to get to this, but I think we need to do it now. So I'm going to use, there's no element up here with a single X as its symbol. So I'm going to use an X as a generic. That's our generic element. Right? We do have an XE, right, xenon, but we don't have a single X. So it's safe for me to use. So there's our element symbol. The symbol is surrounded, it has four corners, right? Each one of those positions is reserved for certain types of information. Okay? First of all, I better, before I can do this, I have to define my terms. Okay. So, atoms have a nucleus, and then they have a space around them. the nucleus can be occupied by positive particles, or protons, okay, and neutral particles called neutrons. Okay. They're about the same mass, but this one has a charge and that one doesn't. And then this space out here is occupied by negatively charged particles called electrons. And these electrons, while they have equal and opposite charge to the protons, they don't have the same mass. Electrons are about 1,800 times smaller than a proton in mass. Okay? So don't ask me how that happens. It's got a full charge, opposite charge, but doesn't have the mass. Now, how do we define an element? An element is defined by the number of protons. So this number, the atomic number, is the number of protons for each atom in that element. Okay? If we change the number of protons, we've got a different element. Okay, so that's this position right here. That's where we put the number of protons. Okay, let's do an example while we're at it. Oxygen. So it's going to have 8 protons. See right here. This position is reserved for the summation of the number of protons and the number of neutrons. Right? It's called the mass number for the element. For oxygen, it varies, but most of the atoms of oxygen have a 16th. Okay, so if we have 8 protons and 16 protons plus neutrons, how many neutrons do we have? 8. 16 minus 8. If this is the total, and that's the proton, then you just subtract one from the other and you get the number of neutrons. Okay, so we have 8 neutrons. This position is reserved for the number of atoms in a compound.
Is that number always going to be even?
Yes. Yeah, be whole numbers. I'll explain later why you got these fractions. Okay. So the number here, so oxygen in the atmosphere, right, it's one of the diatomics, right? So oxygen by itself is going to have a 2 there. That says there are 2 oxygen atoms hooked together, that's your element. But each one of them has 8 protons, and we have chosen we call it an isotope. We have chosen the isotope that has 8 protons and 8 neutrons. Okay? Now, if there is a charge, it goes up there. So I can't put a charge there because O2 it never has a charge. But if I pick something else like sodium, its preferred charge is +1. And it'll have 11 here, and the most common isotope is 23. Right? Now, if there's only one of them, we never write 1. That's just redundant. If you got a symbol there, you got at least 1. So that's the position. That's what happens around the position. These are reserved for that information. Now, you won't always have to put that one and that one in there when you're writing compound, right? Because maybe you're using a naturally occurring oxygen, and it's going to be a mixture of isotopes. So it doesn't make any sense to put a number up here because you don't know. You only know that it's the naturally occurring mixture, so it has several different isotopes, so you just leave that blank. And if you have the symbol, you know that one, right? If I write CD for cadmium, I know it has 48 protons. It has to have 48. Otherwise, it's not cadmium, okay? So this is just when we're being explicit. All right. So now, we go to a discussion of how do we know this stuff, okay, right? Well, there were theories. You see. I'm going to have to back up. I accidentally punched all the buttons. Let's see, let's go back. All right. See, did I miss anything? No. There. Rules for writing formulas. I did miss that part. Let's back up some more. Come on. There we go. No. There we go. So when you write a chemical formula, you just write the symbol. And if you write one of them, that means there's one atom of that element. And with this position, we say, well, there's one of those and three of these together in that formula. Okay? It's really simple. So let's take this example. DDT. Everybody heard of DDT? It's an insecticide. It's probably the one insecticide that was responsible for saving millions and millions of lives because it is so effective at killing mosquitoes, and the diseases that they transmit, like malaria, like yellow fever. They're deadly. So DDT was sprayed, just the earth was blanketed with it. And they would even, I've seen movies of people being sprayed with a hose, dusted with DDT. It's that safe for humans. Of course, in the environment, DDT breaks down into this product. That's the bad one. That accumulates in upper level predators. And particularly, it's bad for birds because it weakens their shell. And then when they sit on it to nest, they break the shell, and that's the end of that. It's called, the ecological term is called trophic amplification. So it's persistent in the environment as this, plus it makes that one, which is much, much more toxic. And it gets into the food chain, and microscopic animals eat the plankton, and then something eats them, and something eats them, and something eats them. And every time that happens, they concentrate this stuff because it's fat soluble. So it sits there in the adipose tissue of animals as you move up, and any predator naturally goes for the high energy part of its prey. So that's why when a cat kills a chipmunk or a mouse, first thing it does is eats the head because there's so much fat in the brain. Very high energy. But that's where this stuff resides. It dissolves in fat. And when you do that, then you take that in and you keep, and you eat, and it just concentrates in your system. So trophic means to eat. So it's amplified in its concentration by eating, trophic amplification. And the top predators, like for instance, the bald eagle, when they eat their fish, those fish have been eating smaller fish, and they've amplified it, and so the eagles amplify it, gets into their system, female lays an egg, and the shells are really weak because of this, and that's the problem. So DDT was banned. Now we saved a bunch of eagles, but we caused millions of people to die because we didn't have a good substitute for it to kill the mosquitoes. Anyway, DDT. So let's say DDT has 14 carbons, 9 hydrogens, and 5 chlorines. So it got carbon and hydrogen and chlorine. So they're your symbols. Right? So how many of each? We have 14 carbons, right, in that position, and 9 hydrogens and 5 chlorines. So that is the molecular formula for DDT, right? We don't know how those are combined, you know, how they're stuck together. It doesn't say anything about their structure. It just says we have that many, and that many. And that's a lot of information, but it's incomplete. Okay, how do we know about these, the structure of the atom? Let's see, how am I doing on time? 9 o'clock? We're good till 9:40. Okay. I'll be sure I get done. I better pick it up a little bit. J.J. Thomson. J.J. Thomson postulated that the existence of electrons, these negatively charged particles, based upon his work with the cathode ray tube. By this time, end of the 19th century, cathode ray tubes were easily produced. They're just an evacuated tube with an electrode at one end and a phosphor screen at the other. So once you turn it on, you produce electrons at one end and they smash into this phosphor screen, and normally they go in a straight line because you have a system over on one side called a collimator, and it takes the particles that are emitted by this electrode and makes them go in a straight line. You got 2 plates like that, and you got this source of electrons here, and they're just going off in all directions. Right? So the ones that go through here, if they could do like that, so they're still diverging. But in order to get through the second plate, they pretty much got to be going straight. So you can produce a straight beam of electrons. Now, and you have a detector over here. So when it hits that plate, you get a spark. Now, how do we know that they were negatively charged? Well, we knew electricity, and we knew that they responded, like the relationship between electricity and magnetism had been established. So we're actually starting to produce electric motors. And J.J. Thomson did some work with magnetic fields, and whenever he brought a magnetic field, a positive side of the magnet made it bend one way, and the North Pole went one way, and the South Pole went the other way. So he knew he had a charged particle. And he postulated that these particles were negatively charged, and he called them electrons. And there's this is a recreation of his cathode ray tube. So William Thomson, also known as Lord Kelvin, same guy that invented the Kelvin temperature scale, proposed this model. So we knew that atoms were neutral because you could bring a charged plate close to them and then nothing happened. Right? So neutral atoms means that you have to have a balance of positive and negative charges. Right? So the proposition was that you have the same number of electrons as protons in the element. They got that right, so that they could balance their charges. But we didn't know where those charges resided in the atom. So this one model the plum pudding model says that this sphere of positive charge was sprinkled with electrons. And that's how you got your balanced charge. So they call it plum pudding because these guys are English. And I guess they knew what plum pudding looked like. So when you say plum pudding, oh yeah, I know what that means. The little pieces of plum are the electrons. So, Ernest Rutherford was able to prove that the plum pudding model was wrong. There was a competing model. It was called the nuclear atom, where the positive charges resided in a small central nucleus, and the negative charges just were out here around it, like the one I drew earlier. So he proposed an experiment that would prove or disprove one or the other. They couldn't both be right. So his experiment was called the gold foil experiment. And he knew that if the plum pudding model was correct, that the alpha particles, which are basically helium nuclei, were fired at the target, this very thin gold, and if the plum pudding model were correct, the mass would be scattered. So the particles would go straight through it because you could hammer gold really thin. It's like just 2 or 3 atoms thick. So it wouldn't, supposedly there would be nothing there to stop the alpha particles from going straight through. He had detectors out here, detectors all around where you could measure, you could see the impact of those particles as they go through the gold foil. Well, if the plum pudding model were correct, they'd all impact right over here on that one spot. Just have a bright spot right there. No deflection. But if the nuclear atom were correct, most of the mass of the atom were in a nucleus, then if one of these particles missed the nucleus entirely, you get that spot. But if the alpha particle came close to, say, a glancing blow or even a direct hit on that dense nucleus, it would bounce off or bounce back. And that's exactly what he got. He detected a small number, but a significant number of impacts were deflective. So that disproved this one and confirmed the nuclear model. Okay. That's just an animation. Oh, another animation. Well, maybe we want to see that. Do we want to see that? There we go. Most of them go straight through. Some of them hit the nucleus. Okay, enough of that. Okay, so we got Dalton's atomic theory established that the atom was a solid particle, and it was the smallest that you could get for an element. If you had a pure element and you kept picking it apart, eventually you'd reach the atom. Thomson, of course, identified the electron, so he said, okay, now the positive and negative charges, they have to be neutralized. My model is the plum pudding model. But Rutherford said, no, it's a nuclear atom, and proved it. Right? So now we have most of the mass in the nucleus, and for the positive charge, and the electrons are out here in space. But that wasn't good enough either, because it didn't explain certain types of behavior. For instance, the electron microscope. Why does the electron microscope work? It doesn't work because the electron particles or smashing into your target. It works because electrons behave also as waves. So you have the particle wave duality of matter, just like you have the particle wave duality of light. That's why electron microscopes work. So we needed a new theory. So the modern concept of the atom says electrons are actually energy waves that are out here around the atom. But they can also be treated as particles sometimes. So that's the problem with that duality concept. Sometimes you have to treat them as waves, and sometimes you have to treat them as particles. Okay. We haven't been able to resolve that one yet. And in fact, Heisenberg was a mathematical chemist who said that, in his uncertainty principle, he said, when you measure something, when you observe something, you're actively influencing either where it is or how fast it's moving. So if you want to find out where it is, then you can't tell how fast it's moving. If you want to know how fast it's moving, you can't tell where it is. So, so electron positions now are described in terms of probabilities. In other words, when we say the electron cloud is this shape around the atom, we're saying, okay, that's the highest probability of finding an electron is in that region. But if it has higher energy, it might be out here, a different probability, right? We can't say it's here, here, or here. We can say the highest probability is in this region. That's the best you can do. Okay. So Rutherford had a graduate student who became, after graduation, stayed with his group, named Chadwick. And one thing they noticed was that the number of protons did not account for all of the mass of the atom, right? It accounted for a large part of it, but it didn't account for all of it. You know, usually 50% or less of the mass is accounted for by the proton. So there was obviously another particle in there, something else adding mass to the atom, but it didn't have a charge because we've already accounted for the charge in the protons and electrons. That's covered. So Chadwick set to work on finding out what this particle was, and eventually they identified it as a neutron. The neutron is also in the nucleus, but it has no charge. It just adds mass. Well, it does more than that, but for our discussion here, it adds more mass to the atom. It's only slightly more massive than a proton. And for simplicity's sake, you can say that they're the same mass. Okay, so now we know that electrons are part of the atom, and they're outside the nucleus, negatively charged. Protons reside in the nucleus. They're positively charged, and they're accompanied by neutrons in the nucleus. So the most common nuclei for our elements are going to have in the neighborhood of, for every proton, there's a neutron, up to a certain point. And then as you get bigger and bigger and bigger, the nucleus, you need more neutrons. The neutrons have a stabilizing effect on the nucleus. If you don't have enough of them, then you get an unstable nucleus and there's radioactivity. Or if you have too many, similar problem. So there's an ideal number of neutrons for the number of protons, depending on where you are, for stability's sake. Okay. So there's a relationship. If the electron is relative mass 1, the proton is 1,800 times heavier, and neutron similar, 1,800 times heavier. So the electron is virtually weightless. So why do different atoms have different chemical properties? Well, think about how we establish the chemistry of an element or an atom as part of an element. Well, you have to react it with something, right? I mean, if it's just sitting there, you don't know anything about it. Well, you could get physical properties like mass and volume, temperature, and things like that. But chemical properties, you got to react it with something to know anything about its chemistry, right? So if we've got two atoms coming together to form a reaction, what's the first thing they're going to see as they get closer and closer? They see the electrons, right? So it's the interaction of the electrons that form the chemistry of an atom. And when those electrons, when the atoms get close enough, you either get, the electrons either are shared between the two, or under certain circumstances, one might be a stronger pull on the electrons than the other one. So it'll strip one or more electrons away from the other one. So that would make this one negative, and then you take electrons away from this one, that would make that one positive. Right? Before it was neutral, right? Same number of protons, same number of electrons. So if you take electrons away, you have an imbalance toward the positive. If you add electrons, you have an imbalance toward the negative. That's how you get, I'm sorry?
So is that the same thing as polarity?
Yep. That's how you get ions, by the electron transfer. You can't mess with the protons. What happens if you change the number of protons? You get a different element, right? So ions are always formed by the movement of electrons. Okay. We mentioned isotopes, and an isotope just means that when you compare one atom to the next, what are you going to see? Say we have a chlorine. Say we have a chlorine, and this atom has 17 protons. This one also has 17, because they're both chlorine. Let's say this one has a mass number 35, and this one has a mass number 36. So how many neutrons does this one have? 18, right? How many does this one have? Did I do that right? Yeah, 18. This one has 19. Okay, that's the difference between isotopes, the number of neutrons. Now, they have the same chemical behavior, right? Because they have the same number of protons and the same number of electrons when they're neutral. So they behave chemically same, but they're different atoms because they have a different number of neutrons. Okay? Now, when you get a certain combination, say we have equal numbers of this one and this one in the naturally occurring sample, then this one is going to influence the mass as 35, and this one influences the mass as 36. So if you have roughly equal, then the mass is going to be somewhere in between when you measure them as a group. So it'll be 35.5 or thereabouts. Well, chlorine, as it turns out, is about 35.5, naturally occurring chlorine. So it has roughly equal distribution of this isotope and that isotope. Okay, it's kind of like doing your GPA. It's a weighted average, right? So the for other elements, one might be a major amount, like 95, 98% would be that isotope, and just a little bit of influence from the others. So that's what you want with your GPA. Most of them you want to be A's, and then a few lesser, right? Gives you your weighted average is more toward this one. That's what you want. Okay, so sodium was the example there. And here's the discussion of positions for the atomic number and the mass number. There's carbon. Now, as it turns out, carbon is our standard. So the isotope, that is carbon, 6 protons, and 12 mass number, that's our standard. Everything else is measured against that. Okay. Used to be oxygen, but oxygen was a little more difficult to handle because it was a gas, it was diatomic. Carbon is much easier to produce in pure form. Right? All you have to do is take any carbon-based compound and pyrolyze it. That is, heat it up really hot so that you drive off all the elements except carbon. Okay? You don't want oxygen in there, right? Because that'll consume the carbon. But if you pyrolyze it, it is heated up in the absence of oxygen, then you get carbon left over. Nothing but carbon. And then if you have a mass spec, you can separate the carbons into the various isotopes. Most of them are this and this. C14, C13, C12. This is the lion's share, and this one is radioactive. Right? So that's the one we use for carbon dating. Anything that used to be alive, you can use carbon dating. Up to about 10,000 years old. Anything past that, the half-life limits how far you can go.
So if it's more than, and how do you know it's radioactive? Without looking at that. Okay.
You don't know from looking at that. I just told you. Carbon-14 is radioactive. It decays. See, it's got extra neutrons, and that makes the nucleus unbalanced. So it decays to reach a more stable form. This one is, these two are perfectly stable. Okay. So, let's see. Let me get through this chapter. So what's the mass number of this isotope? It has 23 protons, 28 neutrons. The mass number is the sum, right? So it'd be 51, right? 23 protons. What element is it? Vanadium. Vanadium. Right? With a mass number of 51. Now, periodic table. Where did it come from? Well, Mendeleev was a Russian educator, but he was curious, and he noticed that certain elements had similar properties to one another, so he put them in groups. He used to call them families. They had similar characteristics, so he grouped them together. And in his original table, he grouped them from left to right. But now we group them up and down. So these, for instance, are the noble gases, and they have similar behavior. In other words, they don't play well with anybody. They don't form compounds. Well, you can force them. You can force some of these, but under normal circumstances, they don't form compounds. But they're all similar. The alkali metals, they're all similar. Sodium, potassium, rubidium, lithium. Hydrogen's stuck over here because it doesn't fit anywhere. So we just put it over there for balance. But they have similar characteristics, chemically speaking. These have similar characteristics. So Mendeleev noticed that they were like that, and that the groups, when you put them side by side, he noticed that you could progress through characteristics through the groups, and then if you focused on one layer, then you reach a certain point where you can't go any further this way. Because if you do, you're back at this one again. That's called a period. So you go through a period and you wind back around and start over again. Wind back around and you start over with a group where the characteristics are similar. Later on, they rearrange things and put things in a vertical group. Now, why does Mendeleev get credit for the periodic table? Because there were others working on grouping elements together. Lothar Meyer was a German, and he found that there were triads. In other words, groups of threes. You know, that's as far as he went. Mendeleev gets credit for periodic table because he predicted. He noticed that there were places missing there, where as you progress through a period, there should be something there. Because if you go to the very next one and move it in here, it didn't match up with characteristics. So he said, I'm going to leave a hole there and just move this one over into a group where it's more family oriented. So he predicted that there would be, these holes would eventually be filled by discovered elements. And not only that, he predicted what their properties would be. And he was right every time. Eventually they found them, plugged them in those holes, and they fit. That's why he gets credit for it, the periodic table, because it's predictive power. That's what the periodic table looks like today, except for these right here, where you see the 3-letter combinations. Those are elements that had been discovered but hadn't been named yet. Now they have names. So they're, instead of 3 letters, they're 2. And it's really kind of dumb the way they named them. 114 means un-quatrium. So that's 114, un-quatrium. Don't give chemists credit for being too original sometimes. But now we have it laid out in this format. But the characteristics that Mendeleev came up with of our table, where you group things together, that's still there. How do we know atomic numbers? Well, there was a young chemist called Henry Moseley. He was an Englishman. And he was doing work on this X-ray spectra of elements. So he would excite them up to the point where they had so much energy, they would emit that energy as X-rays. And he noticed that as you progress through the elements, as you go from this mass to that mass to that mass, he could take one whole number and plug it into his formula, and it would tell him the wavelength of the X-ray that it would produce. And that whole number he called the atomic number. because it was characteristic of that atom. Now, he didn't know at the time, but that atomic number now we know corresponds to the number of protons. Unfortunately, Henry Moseley, I don't know if they had the draft or not, volunteered during World War I to go off and fight for his country, England, and he never came back. So that was the end of his chemical career. Okay, just a few more minutes, and we'll do generalities. We've identified groups, and some of these groups have names, right? And when you start filling out your extra credit periodic table, there's a place in there for some of the names. Alkaline metals, alkaline earths, noble gases, halogens, right? So convert halogen lamps. They put one of these, usually iodine. That's why these lights out here are kind of yellowish green, and they have iodine in them. The chalcogens, C-H-A-L-C-O-G-E-N, chalcogens are the oxygen group. The pnictogens, it starts with a P, but the P silent. P-N-I-C-T-O-G-E-N, pnictogens. And the transition metals, all of these guys are here. Now, the periodic table itself is divided by this line, goes right down here, that you see on this side, you have non-metals, on this side, you have metals. So most of the chart is metals, from here over. Non-metals are here. And they have general characteristics of metals, like metals are malleable, shiny, conduct electricity, blah, 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 a whole bunch of them.
The bottom two rows, they form metals too.
Yeah, because this one has stuck right in here, right? We just extracted it out here, and this one is extracted from that place. The only reason they're out here like that is so that our table is not 20 feet wide. Okay, make it more compact. But you'll notice this jumps from 57 to 72. We stick these right in there. We stick these right in here. But they're metals. Non-metals, they're usually dull. They don't conduct electricity, generally speaking. We talked about groups and families. They have similar chemical properties. Periods are the rows, left to right. So you get down to one end, that's the end of this period, you gotta go back to the beginning, start over again. But the periods are arranged so that the groups line up. Let's see. There are different types of periodic tables. This one only gives you the modern new numbering system for the groups. Left, right, 118. Some older charts include a system where 1A, 2A, 3, 4, 5, 6, 7, 8A are here and these two, and then over here. And then the B's go in here. This system is useful. Has anybody had anatomy and physiology? Okay, so we talked about the octet rule. The octet rule. This allows you to say, what are the number of valence electrons? In other words, the electrons in the outermost shell that do the reacting. Right? So this one has 1, that one has 2, this one has 3, 4, 5, 6, 7, 8 in the outer shell. Right? And the octet rule just means that everybody's trying to look like noble gases. They all want 8 electrons. So if they can react with some other atom and get those electrons so that they think they have 8 in their outer shell, that's a driving force for the reaction. Now, there are some in here, germanium, silicon, arsenic, antimony, tellurium, polonium, right in here, that are very close to that dividing line. Sometimes, under some circumstances, they behave like metals, sometimes they behave like non-metals. So we call them metalloids. But if you only have two choices, metal, non-metal, non-metal, metal. Okay? Most elements in their purified state are very reactive. That's why you don't find metals in nature, pure metals, or pure elements in nature, because they're very reactive. The fact that we have 20% oxygen in our atmosphere is good for us because we need it to live, but it's not real common in the universe to have that much oxygen because it's very reactive. There are exceptions, like gold. That's why they call gold one of the noble metals. In other words, it doesn't form compounds easily. Silver is more reactive than gold. Platinum is a noble metal. Palladium is a noble metal. So you can find them uncombined, pure elements in nature. Okay, diatomics. The diatomic molecules, well, diatomic elements are the ones I showed you. Diatomic molecules means that there are two atoms in the compound, like sodium and chlorine, table salt, sodium chloride. So that's a diatomic. That's two atoms. So these are your diatomic elements. And notice the diatomic elements are all nonmetals. Hydrogen, of course. If we put it over here, it wouldn't fit there. So we put it over here and just say, all right, hydrogen is a special case. But all the diatomics are nonmetals. Now, there are various forms of elements, right? Other than the diatomics, good example is carbon, right? Carbon can take several forms. Historically, of course, a diamond, it's one form of carbon. It's just pure carbon with some impurities. You know, if you have a blue diamond, it has inclusions of other elements that give it the blue color, but pure carbon is just colorless as a diamond. Graphite is another form of carbon. Okay, it's an allotrope, but still an element, but it's a different structural form. The fullerenes, one of the first ones discovered was Buckminster fullerene. Sometimes they call them buckyballs. They're 60 carbons in the shape, it's kind of like a geodesic dome. You've seen pictures of Disney World, that Epcot Center, kind of like that. The buckyball is carbon in a network that forms 60 carbons that forms that ball. There are other forms of carbon, like nanotubes, right? Just carbon in a tube. Nanoparticles, right? So they're on the scale of 10 to the minus 9th meters, right? So they're very small, and they're used in various things like sports apparel. Have nanoparticles in them. These what do they call them? Those copper compression hosiery. They have nanoparticles in them. Okay. Oops. Go back. There's your buckyball. There's your nanotubes. Now, carbon, being a nonmetal, is, generally speaking, non-conductive. In fact, the thermal conductivity of diamond is extremely low. So when you go to the jewelry store and they want to see, is that really a diamond? They bring out this device and they just touch it to your diamond and it measures the thermal conductivity of the gem. And if it's too high, it's not a diamond. Diamond is the least conductive of all the gems that they're going to investigate. So they just stick it on there and see what it is. My wife got a ring from a friend who said, just send me the shipping. I'll send it to you. This person thought it was a, what's that blue gem from East Africa? I can't remember the name of it right now. It's not a diamond. So it arrived and we were just in the mall. So we went by the sales, said, look at what we got. Said, and the sales lady says, isn't that a beautiful blue diamond? What? It's not a diamond. He says, well, let me check. So she got her device, put it on there. Yeah, that's a diamond. So we got a carat blue diamond for the cost of shipping. So we said, we're not leaving with this thing. Take it, send it to your gemologist, get an official appraisal so we can take it to our insurance company and insure this thing because then we know it's worth some money. Okay, ions. So I mentioned earlier how you form ions. You do it by either adding to or removing electrons from a neutral atom, right? So if you add electrons, like for the halogens, you add one electron to chlorine, you get a Cl minus ion, right? So if chlorine is 17 protons, how many electrons would it have to give you that minus charge? 18 electrons, right? One extra. If we're going to form table salt, then sodium is going to be positive 1 charge. So how many electrons would it have? 10, right? It has 1 extra proton that's not neutralized. That makes it a positive 1. And then sodium chloride forms a compound by electrostatic attraction. Sodium attracted to chlorine. Once you transfer that electron from here to here, you get ions, and then the ions attract electrostatically. That's one type of compound, ionic. Okay, let's see. So we've gone over that. Now, generally speaking, when metals and nonmetals combine, they form ionic compounds. They do it this way. And when they do that, each group has a characteristic charge. So in this case, they always form a +1 charge. First group, +1. Second group, +2. Skip these, and +3, +3, +3. Ooh, it gets wishy-washy in here. Those are definitely +3s. But the other side, these don't form ions. They don't form compounds. So they're zeros always. But these are -1, the halogens. So 0, -1, -2, -3, and then kind of indefinite. So remember those rules. Halogens, actually we should have gone over here. -1, -2, -3 when combined with a metal. Okay. When it's combined with a non-metal, that's a different story. And we'll cover that. Now, you'll notice also in that periodic table that I gave you that, where is it? Here it is. You'll notice that in the upper right-hand corner of each one of these cells is a list of charges. These are available charges for the element. They're not definite, they're available, right? So you'll notice that all of these alkali metals, they're always that one charge, never anything else. Alkaline earths, they're always the 2+ charge. The halogens vary a lot, right? But until you know different, consider them -1. Okay, oops, we're out of time. Let's see. Did we finish? We came close. Yeah, that's close enough. So Thursday we'll get chapter 5, nomenclature. How do you name these things?
Ooh, that's fun. So the next thing will be on 4 or 5, and will there be any other chapters?
Nope, just those 4 or 5.
Got it. I finally got syndicate worked out last night. Me and my mom were up until like 9 or 10 trying to figure it out, emailing people. But we got it figured out so now I can read and take the test for the past one. Or the homework.
Okay.
So hopefully I'll get that done either today or tomorrow, and then I can work on this chapter.
I checked this morning and everybody is in there through Blackboard.
Through Blackboard?
Yeah, you got to go through Blackboard.
Okay, I'll try. I've got it to where I can go through the Synergage website. I'll try. It might be easier through Blackboard.
Yeah, just go. Yeah, just go into Blackboard and under Start Here, just look down and you'll see a Synergage link. Go to that link. It may ask you to enroll again because it treats it as if it's a completely different course.
Oh, okay.
Okay. So don't do any work on the Synergage site. Do it
Through the
within Blackboard. That way the grades are automatically dumped into your grade book.
Okay, so what you can see and all that.
Yeah.
So definitely go through Blackboard then. Okay.
Yes, please.
Got it. Thank you.
You want me to take a test that?
Wherever you're comfortable. We've got this room. Nobody else is in here, so you can, rather than pack things up, you can just sit right back down.
What do you say?